Bismillahirrahmanirrahim. So, dear students, today we have an important topic in the organometallic chemistry, that is the effective atomic number rule in the metal carbonyls. It's also sometimes referred to as the 18 electron rule. So, what is this actually? Let us move. Okay, so let me first go the definition. Metal carbonyls किसको कहते हैं? So metal carbonyls are the compounds where the ligand is carbon monoxide. So ligand is metal. The ligand carbon monoxide is it coordinates with the metal. So this is called as the metal carbonyl. ठीक? For example, you have this hexa carbonyl chromium. So carbon ligand bonded with the chromium, like the pentacarbonyl iron, likely tetracarbonyl nickel. So there are many examples. ठीक? Now this is all about the metal carbonyls, the bonding between carbonyl and the metal, or carbon monoxide with the metal. Now what this atomic number rule says, effective atomic number, EAN rule. So it tells us the sum of electrons on this central metal, whether the metal is in the atomic form or ionic form, and the electron is donated by the ligands in a coordination complex. Okay? So I can just show you this how we actually write this. So this is basically the number of electrons on the metal, whether metal is in the atomic form or the ionic form, plus the electron is donated by the ligands. So effective atomic, and this for stable complexes, it is generally equal to the atomic number of the next incoming noble gas. Now if this number, the sum of electrons in the central metal atom or ion plus the number of electrons donated by the ligand, if this number is equal to noble gas, the complex becomes more stable. So this is your effective atomic number. Now how it is called 18 electron rule? If we apply the same rule here, but what we'll do, we will not talk about this the electrons of the central metal, and rather the number of electrons in the valence shell. So if we are interested in calculating the number of electrons in the valence shell of metal, plus the number of electrons donated by the ligands, now then it is called as 18 electron rule. So whether you say effective atomic number rule or 18 electron rule, the results are one and the same. Now even though this rule is very helpful in predicting the stability of organometallic complexes or the carbonyl complexes, but there are many limitations. Let's see. Limitation number 1. Bulky ligands force the complex to have less electrons than. Now if the ligand is bulkier and then you apply this rule on the same complex, then what happens is that the bulky ligands, they force the complexes to have less electrons than. So you will calculate the effective atomic number rule, but in the actual sense the number of electrons will be less. Number 1. Effective atomic number rule fails when the bonding of organometallic clusters of moderate to big size. So if ये जो organometallic complexes होते हैं, जो clusters होते हैं, sometimes they have 1000 atoms, they have hundreds of atoms. So when the cluster is larger, then this rule you can't apply. Likely point number 3. This is second point number 3. The rule is not applicable to organometallic compounds of main group metals. So if in the metal complex the metal is a main group as well as it belongs to lanthanide, aconite, you cannot apply this rule. And then counting the electrons helps to predict the stability in the metal carbonyls, but it doesn't tell us whether the carbonyl is bridged or terminal. Now in the organometallic this carbonyl complexes, there are many types of carbonyl ligands. Sometimes carbonyl acts as a bridged ligand, sometimes acts as a terminal ligand, but this rule doesn't tell us anything about that case. So this is some of the limitations. Now let's move to our original topic. How can we calculate the effective atomic number of a complex? So the point number 1, what we have to do, the electron is present in the valence shell Nd or Ns or Np of the central metal, they are counted. So first of all we have to count the electrons in the valence shell of the central metal atom, and then the electrons are added to it or subtracted to it depending upon the charge of the metal present on the metal carbon. So then to that particular electrons which are present in the valence shell, So those we have to subtract the electrons depending on the charge. So on the complex, then each carbonyl, if the carbonyl contributes as a ligand, it contributes 2 electrons to the valence shell. So these 2 electrons we have to add. And if the carbonyl acts as a bridging carbonyl, if it's like a bridge, you can see here MCOM, then it contributes only 1 electron. And if you have a metal bond present in the carbonyl complex, then each metal contributes 1 electron. So these are basically the 4-5 rules by the help of which we can calculate the effective atomic number of any complex, and to some extent we can predict the stability. Now all this I have tabulated it here, so let's take these examples and we'll understand this. I can show you just a shortcut. How can you remember? So effective atomic number is basically Z minus ON plus twice Cn. Now this rule you can remember, but this rule is applicable to only when the carbonyl is not in the bridged form. This is the atomic number of the central metal Z minus the oxidation state. Calculate the oxidation state. This is important. Plus twice the coordination number of the carbonyl. But important thing is that it should not be bridged. You can use this formula. Now let us apply these rules. This is a complex chromium. It is bonded with 6 carbonyls. Now you see there are tables. This is one table. This is another table. This table is as per the 18 electron rule. And this tabulation, this is as per the effective atomic number rule. This one. The results will be same. For example, this is our complex carbonyl complex, hexacarbonyl chromium. Now first of all, the total number of electrons on the metal chromium. So what is the atomic number of the chromium? Because atomic number means number of electrons. Scandium, titanium, vanadium, chromium. So there are 24 electrons. But if you check its valence electrons, there are 6. Scandium, titanium, vanadium, chromium. So this is your 3d, 4 and 4s2. So 3d, 4 and 4s2 will give 6 electrons. So this is as per the valence. This is the total number of electrons. Now carbonyls are there 6, and all these are terminal carbonyls. So they are like this. This is metal. It is bonded to carbonyl simply. Now the carbonyl will contribute 2 electrons. So 6 carbonyls to 6 into 2 is 12. There also you can write 6 into 2, 12. Now you add this and this, that gives 36. Fine. And this gives 18. Now this gives 18 because the number is 18, so the complex is stable. And here it gives 36, and 36 is the nearest noble gas. So when 36 is the nearest noble gas, so that means this complex attains stability. So, so we can write down that so this 36 basically is your krypton. So when you calculate the effective atomic number, if the counting of electrons comes equivalent to the noble gas, next noble gas, the complex is highly stable. So this way we have to apply. It's very simple. Now let's take some different complex now. Okay, let me just show you this one, second one. This is a complex where carbonyls are 5, but there's a negative charge in the complex. So manganese, the total number of electrons in the manganese is 25. Now how it is 25 now? Now this is because you have minus charge here. See, first of all, scandium, titanium, vanadium, chromium, manganese. So manganese is a D5 complex, 5. So D5 complex, so this is 25 is the number of electrons. D5 and NS2, so 7 you can write here. 5 carbonyls, 5 into 2 is 10, 5 into 2 is 10. Now charge is -1, so you can put -1 charge here. Okay, so this 25 was atomic number. Put -1 charge. Here put 1 charge. So this comes 18, stable, and this comes 36, that's stable. So this is how you can go further if you have this charged complex. But if it's plus charge here, then that plus you have to subtract. Now one more example, which is a different example, where we have 2 metals, and then we have a concept here. We have a metal-metal bond. Now in these cases we have to be careful, because we don't know whether there's a metal-metal bond, but we can just guess here. since there are two manganese, so there will be one metal-metal bond. But it is not necessarily that every time you have a Mn2 and then there's metal-metal bond. It depends. But in this case, we have a metal-metal bond. So calculate the total number of electrons in the manganese. There are two manganese, so 25 into 2, that is 50. Carbonyls are 10, so that is 20. So here also you can add the valence electrons, 7 into 2. 2 carbonyls, 20. One manganese bond, so each manganese contributes 1 electron, so that's 2. There also you can write 2. So if you check all this, that becomes, so you see 36, but 36 by 2 you have to do because there are two metals, that's 18. And here also you do 30, this is 72 by 2, so you get 36, that is the nearest noble gas. And then, okay, this is another interesting complex, Bridget complex. So here are two iron atoms. Now we don't know there's a Bridget, so but we have to remember this, that we should know the structure because we don't have any other way to calculate it. We should know the structure. From the structure we can predict there is Bridget carbonyl. So there is basically a Bridget carbonyl. So Bridget carbonyl means something like this. Sometimes it can be 2 also, sometimes 3 also. It's like this. Carbonyl in the form of bridge. There's carbonyl in the form of bridge. And then there's metal here. And sometimes there can be 3 bridges also, sometimes 1 bridge, depending. So this is how the bridge acts. Okay, so this Fe2CO whole 9. Number of electrons on the 2 iron atoms. Each iron atom is number 26. So 26 into 2, 52. Number of valence electrons 16. 8 into 2, 16. There are 6 carbonyls, so this 6 into 2 is 12, 6 into 2 is 12. Now we have added for the 3 COR bridged here. So basically there are 3 bridged carbonyls. This is CO here. So there are 3 bridged carbonyls. As I mentioned, this only we can predict from the structure. The rule can tell us nothing. So if there is bridged each, then bridged carbonyl, so this is 3 into 2, that is 6. 6, you have to write 6 here. And in addition to this, there is metal-metal bond also. So you have to have metal-metal bond is also there, this metal-metal bond. So metal-metal bond, each metal contributes 1, so this is 2. And there is 2 here. So if you add this, you got 72 divided by 2, 36. 36 by 2, 18, and then this is stab. And this way you can calculate the effective atomic number of all these for your exercise. Okay? So again you can look at these rules. The electron is present in the valence shell. Now when you say valence shell, that means you are basically dealing with the 18 electron rule. But if you are looking at the effective atomic number, then you should not look at the electron in the valence shell, but the total number of electrons in the metal. And then if you have a negative charge on the complex, you can add that. And if you have a positive charge, you can subtract that. Each terminal carbonyl will give you 2 contribution. The bridged carbonyl, that will contribute 1 electron to the valence shell of each atom by attaching it. And the metal-metal bond will contribute 1 electron. This is all for the day.